Imagine standing on a hill somewhere in what we now call Northern Europe. The year is unknowable. The calendar has not been invented. Writing will not exist for another 90,000 years, and yet something enormous is happening. The air is colder than anything you have ever felt. Not the cold of a winter morning or a frost-covered field. This is a different kind of cold. It reaches into your bones and settles there permanently. You look north and see something impossible. A wall of ice stretches across the horizon. It is taller than any mountain you have ever seen. It is white and blue and ancient beyond comprehension. This wall is moving, not quickly, not in a way your eyes can detect in a single day, but it is advancing. Inch by inch, year by year, it creeps southward across the land. Beneath it, entire forests are crushed, rivers are swallowed. Lakes vanish under ice that is miles thick. The ground itself bends under the unimaginable weight pressing down from above. This is not a storm. This is not a season. This is an ice age. And it will last for tens of thousands of years before it finally, mysteriously releases its grip on the world. Here is the strangest part. This has happened before, many times before. The earth is frozen and thawed and frozen again in a rhythm that stretches back millions of years into deep time. Every 100,000 years or so, the ice returns. It covers vast portions of the planet. It reshapes continents. It drives every living creature southward or into extinction. Then it retreats. And then, like clockwork, it comes back again. The humans alive 100,000 years ago did not know they were living at the start of one of these frozen chapters. They had no instruments to measure the dropping temperatures. They had no satellites to photograph the growing glaciers. They had no written records describing previous ice ages. They simply experienced the world growing colder, the winters growing longer, the animals migrating farther. They watched the landscape change around them. Grasslands turned to tundra. Forests shrank and retreated southward. Familiar rivers slowed to a trickle and then froze solid beneath gray skies. These people adapted. They found shelter in caves. They learned to make fire reliably. They stitched animal hides into clothing that could withstand the brutal cold. Survival demanded invention, but they could not have understood the larger pattern. They could not have known that the earth itself was caught in a vast repeating cycle of freezing and warming. We know now. We have drilled deep into ancient ice and pulled up cores that contain tiny bubbles of atmosphere trapped thousands of centuries ago. We have read the chemical signatures locked inside ocean sediments. We have measured the advance and retreat of glaciers across every continent. We have mapped the scars they left on the bedrock. And what we have found is astonishing. The ice ages are not random. They follow a pattern, a rhythm. Something is driving them with a regularity that suggests a mechanism, a trigger, a hidden clock ticking somewhere in the machinery of the cosmos. For over a century, scientists have tried to understand this clock. They have looked at the sun. They have studied volcanic eruptions. They have examined ocean currents and atmospheric gases. Some theories have been elegant, others have been strange. A few have been remarkably close to the truth. But the full answer remains elusive, tangled in complexity that still challenges our best minds. Tonight, we are going to follow this mystery from its beginning. We will travel back to a time when ice covered nearly half the planet. We will walk alongside the humans who endured it. We will trace the scientific detective story that slowly revealed the pattern hidden in deep time. And we will ask the question that still haunts climatologists and astronomers alike. What hidden clock inside the Earth's orbit keeps triggering these ice ages? What cosmic rhythm dictates when the ice advances and when it retreats? And why does the cycle repeat so faithfully? The answer involves the shape of our planet's path around the sun. It involves a wobble in the Earth's axis. It involves the gentle gravitational tug of distant planets pulling on our world. But it also involves mysteries we have not yet solved, feedback loops we do not fully understand, thresholds in the climate system that can tip the entire planet from warmth into frozen silence. This is a story about deep time, about forces so vast and slow that no single human lifetime can perceive them, about a planet that periodically transforms itself into an alien world of ice. It is also a story about us, about the small bands of humans who lived through these transformations and emerged changed, tougher, smarter, more resourceful, shaped by the ice into the species we are today. So let your eyes close if they wish. Let your breathing slow, and let us begin this journey together, back through 100,000 years of cold and darkness and quiet survival. The ice is coming. It has come before. And in the silence of deep time, the great clock is always ticking, counting down to the next frozen chapter in our planet's long story. Chapter 2. When ice covered half the planet, to understand what 100,000 years ago truly looked like, you must first erase the map you carry in your mind. The continents were in roughly the same positions they hold today, but the surface was transformed beyond recognition. Ice sheets miles thick covered enormous portions of North America, Europe, and Asia. The world was a colder, harsher, and profoundly different place. Begin in North America. A massive ice sheet called the Laurentides stretched from the Arctic down across what is now Canada. It reached into the northern United States with frozen fingers thousands of feet tall. The Great Lakes did not exist yet. They would be carved later by the grinding passage of this very ice. Where Chicago stands today, there was nothing but a frozen plain beneath an ancient glacier. New York was buried. Boston was buried. The ice extended so far south that its leading edge reached roughly where modern-day St. Louis sits, pushing through river valleys and flattening everything in its path. The weight of this ice was staggering. In some places, it pressed the land surface down by hundreds of feet. The Earth's crust itself bent under the burden like a mattress beneath a heavy sleeper. Now crossed the Atlantic. Europe was equally transformed. The Scandinavian ice sheet covered all of modern Norway, Sweden, Finland, and much of northern Germany. It pushed into the British Isles and beyond. Scotland was invisible beneath the ice. Ireland was partially covered. The North Sea did not exist as open water. Instead, it was a frozen plain connecting Britain to the European mainland. The Alps had their own ice caps, and glaciers flowed down from every major mountain range. Rivers that we know today as the Rhine and the Danube ran through landscapes stripped bare by cold. Southern Europe remained ice-free, but was dramatically colder. The Mediterranean coast was habitable, but windy and dry. Forests had retreated to small pockets in sheltered valleys around Spain, Italy, and Greece. These pockets would later become crucial. They served as refuges where plant and animal species survived the worst of the cold, waiting for the eventual warming that would let them spread north again. Now turn east. Siberia was paradoxically less ice-covered than you might expect. The extreme cold meant very little moisture in the air, and glaciers need snowfall to grow. So while Siberia was brutally cold, much of it remained a vast treeless steppe rather than an ice sheet. Woolly mammoths, bison, and wild horses roamed this frozen grassland in enormous herds. The Tibetan Plateau held its own ice cap. The Himalayas were even more glaciated than they are today. Mountain glaciers extended far down into valleys that are now green and populated. In the southern hemisphere, the pattern was different but equally dramatic. Patagonia at the tip of South America was covered in glaciers. The Andes carried ice far lower than their modern snowline. New Zealand's southern Alps were heavily glaciated. Tasmania was connected to mainland Australia by a land bridge because so much water was locked in ice that sea levels had dropped dramatically. This is one of the most important consequences of the ice ages. Sea levels fell by roughly 400 feet compared to where they stand today. Think about what that means. Coastlines extended miles beyond their current positions. Islands that are separated today were connected by dry land. Entire continental shelves that now lie under water were exposed, creating vast plains along every coast. Australia was connected to New Guinea. Southeast Asia was a single enormous landmass called Sundaland. You could walk from mainland Asia to Borneo and Java without ever getting your feet wet. The English Channel was dry. The Bering Strait between Alaska and Siberia was a wide grassy plain called Marinja. This land bridge would eventually allow humans to walk from Asia into the Americas. The oceans themselves were different. Colder water holds more dissolved gases. Ocean currents shifted their patterns as ice blocked northern passages. Marine ecosystems reorganized around the new temperature gradients. Coral reefs that thrive in shallow tropical waters were left high and dry as the sea retreated. New reefs formed at the lower shorelines, only to be drowned again when the ice eventually melted. The atmosphere was different too. Carbon dioxide levels were significantly lower during the ice ages. The air was drier. Dust storms were more frequent because vast areas of exposed continental shelf created new deserts. This dust blew across oceans and fertilized them with iron, changing marine productivity. It settled on ice sheets and sometimes accelerated their melting by darkening the surface. Every system was interconnected. The vegetation zones of the entire planet shifted southward. Tundra covered areas that are now temperate forests. Grasslands replaced woodlands. Deserts expanded in some regions and contracted in others. Africa, the cradle of humanity, experienced its own transformation. The Sahara expanded dramatically. Tropical rainforests shrank to small fragments in Central Africa, surrounded by grassland and dry woodland. East Africa, where many early human populations lived, became cooler and more arid. Lake levels dropped. The landscape opened up into vast savannas where human groups had to travel farther for food and water. Yet Africa remained the most habitable continent. While northern lands lay buried under ice, Africa provided refuge for our species. Most of the world's human population was concentrated there. Small groups had ventured into the Middle East and perhaps southern Asia, but the majority of Homo sapiens still called Africa home 100,000 years ago as the Ice Age tightened its grip. The animals of this frozen world were magnificent and strange. Woolly mammoths with their curved tusks and thick fur wandered the northern steppes. Cave bears sheltered in limestone caverns across Europe. Giant ground sloths roamed the Americas. Saber-toothed cats hunted in forests and grasslands. Enormous Irish elk carried antlers 12 feet across through the mists of Ice Age Europe. These creatures were adapted to the cold. They had evolved thick coats, large body sizes, and behavioral strategies for surviving long winters. They were the megafauna of the Pleistocene, and they were everywhere. The world 100,000 years ago was not dead. It was not a barren wasteland. It was teeming with life adapted to conditions that would seem alien to us today. But it was a world defined by ice. The glaciers dictated where life could flourish and where it could not. They controlled the rivers, the coastlines, the weather patterns, and the fate of every species. And the deepest mystery was this. This frozen world was not permanent. It would eventually warm again. The ice would retreat. The seas would rise. The forest would march northward once more. Then, after a relatively brief warm period, the ice would return, again and again and again, as if the planet were breathing slowly, inhaling warmth and exhaling cold across geological time. What could possibly cause such a vast and regular transformation? What mechanism could freeze half a planet and then release it, only to freeze it again thousands of centuries later? Scientists would not even begin to ask this question until the 19th century. And when they did, the answers they found would challenge everything they thought they knew about the Earth and its place in space. Chapter 3. The Strange 100,000-Year Pattern The discovery that ice ages even existed was itself a revolution. For most of human history, people assumed the world had always looked more or less the way it looked in their lifetime. Mountains were mountains, rivers were rivers. The landscape was permanent and unchanging. If enormous boulders sat in strange places far from any mountain, people invented stories to explain them. In Switzerland, farmers called these misplaced rocks erratic boulders. They assumed floods or earthquakes had carried them from distant peaks. Some believed giants had thrown them during ancient battles. In Scotland, deeply scratched bedrock was attributed to the movement of great floods described in the Bible. The idea that ice itself could move, carry rocks, and reshape landscapes seemed absurd. But in the early 1800s, a few observant naturalists began to notice something troubling. The patterns they saw in the landscape did not match the stories of floods or giants. A Swiss engineer named Ignaz Venetz spent years studying glaciers in the Alps. He noticed that the marks left by modern glaciers matched the scratches and deposits found far below the current ice line. He proposed a radical idea. The glaciers had once been much larger. They had extended far beyond their current boundaries. The landscape of Switzerland had been carved and shaped by ancient ice. His colleague Jean de Charpentier expanded on the idea, documenting moraines, erratic boulders, and polished bedrock surfaces that all pointed to the same conclusion. The ice had once been everywhere. But it was Louis Agassiz who brought the Ice Age theory to the world stage. In 1837, Agassiz presented his vision of a planet once covered in a vast sheet of ice. He called it the ice age, the ice time. His audience was skeptical. Many geologists dismissed the idea outright. It seemed too dramatic, too catastrophic, too much like the biblical catastrophism they had worked to reject. But Agassiz was persistent and charismatic. He traveled across Europe, pointing out the evidence. Scratched rocks in Scotland, moraines in Ireland, erratic boulders scattered across the plains of northern Germany. Slowly, the evidence became overwhelming. By the middle of the 19th century, most geologists accepted that there had been at least one great ice age in Earth's past. Then came the next surprise. It was not just one ice age. There had been several, perhaps many. The geological record showed layers of glacial deposits separated by warmer periods with different sediments. James Kroll, a self-taught Scottish scientist working as a janitor at a university, was among the first to seriously investigate why the ice ages might repeat. His story is remarkable. Kroll had almost no formal education. He taught himself physics, astronomy, and geology by reading books during his shifts as a janitor at the Andersonian University in Glasgow during the 1860s. He noticed something crucial. If ice ages repeated, there must be a repeating cause. And the most likely candidate was changes in the amount of sunlight reaching the Earth's surface. Kroll studied the Earth's orbit around the Sun and discovered that it changes shape over time. Sometimes the orbit is more circular. Sometimes it is more elliptical, stretched into a longer oval. This change in orbital shape, called eccentricity, occurs over a cycle of roughly 100,000 years. Kroll proposed that when the orbit was most elliptical, ice ages were triggered. He published his ideas in 1864 and expanded them in a book called Climate and Time. The scientific world took notice. Here was a mechanism that could explain repeating glaciations. But there were problems with Kroll's theory. His timing did not quite match the geological evidence available at the time, and his mechanism seemed too weak to cause such dramatic climate changes. Critics pointed out that the change in total sunlight caused by orbital eccentricity was tiny. How could such a small variation freeze entire continents? The math did not seem to add up. Kroll's theory fell out of favor by the end of the 19th century. He died in 1890, largely forgotten, his brilliant intuition dismissed as insufficient to explain the great mystery of the ice ages. But the question he had raised refused to die. What caused the ice ages to repeat? What hidden rhythm in the Earth system drove these vast cycles of freezing and thawing? Other scientists took up the challenge. They examined ocean sediments and found layers that corresponded to cold and warm periods. They studied cave formations and found chemical signals of past temperatures. The more they looked, the clearer the pattern became. The ice ages were not random. They followed a cycle, and that cycle had a period of roughly 100,000 years. This was deeply puzzling. 100,000 years is a very specific interval. It is not the kind of number you get from random volcanic eruptions or chaotic atmospheric processes. It suggests a clock, a timer, something mechanical and predictable driving the climate system from the outside. Something astronomical, perhaps. Something related to the Earth's position in space. By the early 20th century, the evidence for repeating ice ages was solid. Deep sea cores pulled from the ocean floor showed alternating layers of warm water and cold water organisms stretching back millions of years. Each layer told the same story: warm period, cold period, warm period, cold period, over and over again, with a regularity that was almost musical, a rhythm written in mud and shells. The warm periods, called interglacials, lasted roughly 10 to 15,000 years. The cold periods, the glacials, lasted much longer, typically 80 to 90,000 years. Then the cycle began again. We are currently living in an interglacial period. It began roughly 11,700 years ago. All of recorded human civilization, every city and empire, has existed within this brief warm window. This realization was unsettling. If the pattern held, the ice would eventually return. Perhaps not for thousands of years, but the clock was still ticking somewhere in the silent machinery of space. The question that haunted scientists through the 20th century was deceptively simple. What is this clock? What mechanism in the cosmos keeps such precise time over hundreds of thousands of years? James Kroll had pointed toward the answer with his work on orbital mechanics. But his theory was incomplete. It would take another brilliant mind to refine it and bring it closer to truth. That mind belonged to a Serbian mathematician named Milutin Milankovic, and his work would consume decades of his life. But his story and his elegant solution belong to the next chapter of our journey. Chapter 4. Searching for Earth's hidden climate clock in the city of Belgrade. In the early 20th century, a young Serbian mathematician sat at his desk and began what would become one of the most ambitious calculations in the history of science. His name was Milutin Milankovic. He was trained as a civil engineer, skilled in mathematics and physics. But his true passion was understanding the deep forces that shape planetary climates over millennia. Milankovic had read the work of James Kroll. He recognized the brilliance of connecting orbital mechanics to ice ages, but he also saw where Kroll had gone wrong. The details needed refinement. Kroll had focused primarily on eccentricity, the changing shape of Earth's orbit. Milankovic understood that two other astronomical factors were equally important. Together, the three created a complex and beautiful pattern. The first factor was the one Kroll had identified: eccentricity. The Earth's orbit around the Sun is not a perfect circle. It is slightly elliptical, and the degree of this elongation changes over time. Sometimes the orbit is nearly circular. Sometimes it is more stretched out. This cycle takes roughly 100,000 years to complete, and it changes how much total sunlight the Earth receives. But the change is tiny. Less than 1% variation in total solar energy. Critics were right to question whether this alone could trigger an ice age. Something else had to be involved. The second factor was the tilt of the Earth's axis. Our planet does not spin perfectly upright. It is tilted at an angle, currently about 23.5 degrees from vertical. This tilt is what gives us seasons. When the northern hemisphere tilts toward the sun, it is summer there. When it tilts away, winter arrives. The tilt makes seasons possible. but the angle of this tilt changes over time. It oscillates between about 22 degrees and 24.5 degrees over a cycle of roughly 41,000 years. This is called obliquity. When the tilt is greater, the seasons are more extreme. Summers are hotter and winters are colder. When the tilt is smaller, the seasons are milder. Summers are cooler and winters are warmer. Milankovitch realized that cooler summers might be the key to ice ages. If summers in the far north were not warm enough to melt the previous winter's snow, ice would gradually accumulate. Year after year, the snow would build. Decade after decade, it would compress into glacial ice. Century after century, the ice sheet would grow, spreading outward and reflecting even more sunlight back into space. The third factor was precession. The Earth wobbles on its axis like a spinning top that is slowing down. This wobble traces a circle in space over a period of roughly 26,000 years. Precession changes which hemisphere is tilted toward the Sun during the closest approach to the Sun in Earth's orbit. Currently, the Northern Hemisphere's winter coincides with Earth's close-to approach to the Sun. This means northern winters are slightly milder, and northern summers are slightly cooler than they would otherwise be. 12,000 years from now, the situation will be reversed, making northern summers warmer. Milankovitch understood that these three cycles, eccentricity, obliquity, and precession, do not operate in isolation. They interact with each other, creating complex patterns of sunlight distribution across the planet's surface. Sometimes, the three cycles align to produce especially cool summers in the northern hemisphere. When this happens, conditions are ripe for ice sheets to grow. An ice age can begin. Sometimes the cycles align to produce especially warm summers. When this happens, ice sheets melt rapidly. The glaciers retreat. Sea levels rise. The planet enters an interglacial warm period. Milankovitch set out to calculate precisely how these three cycles change the amount of sunlight hitting different latitudes of the Earth over hundreds of thousands of years. It was an enormous task. Remember, this was the early 1900s. There were no computers, no electronic calculators. Every computation had to be done by hand, using mathematical tables, pencil, and extraordinary patience. Milankovitch worked on these calculations for over 30 years. He computed solar radiation curves for multiple latitudes going back 600,000 years. The work was painstaking and consuming. During World War I, Milankovitch was interned as a civilian prisoner in Budapest. Even in captivity, he continued his calculations. The Hungarian Academy of Sciences gave him access to their library. He sat in that library day after day, computing the orbital parameters of the Earth, translating them into sunlight intensities, building a mathematical bridge between celestial mechanics and earthly climate. By 1920, he had produced his first major results. He published curves showing how summer sunlight at 65 degrees north latitude had varied over the past several 100,000 years. The curves showed distinct minima, periods when summer sunlight was at its lowest. Milankovitch proposed that these minima corresponded to the onset of ice ages. The correlation was intriguing but imperfect. Other scientists were cautiously interested. The German climatologist Wladimir Köppen and his son-in-law Alfred Wegener, the continental drift pioneer, collaborated with Milankovitch and helped publicize his work. Köppen and Wegener saw the value in Milankovitch's calculations. They incorporated his solar radiation curves into their own book on past climates, giving his work wider visibility in the scientific community. But acceptance was far from universal. Many geologists remained skeptical. The geological dating techniques of the early 20th century were too imprecise to confirm or deny the timing Milankovitch predicted. If you could not accurately date a glacial deposit, you could not compare it to the orbital calculations. And without that comparison, the theory remained elegant but unproven. Beautiful mathematics floating without an anchor. There were also competing theories. Some scientists favored volcanic explanations for ice ages. Major eruptions could inject particles into the atmosphere, blocking sunlight and cooling the planet for years or decades. Others pointed to changes in ocean circulation. If warm currents like the Gulf Stream shifted their paths, northern regions could cool dramatically. Perhaps the ice ages were driven by the oceans. Still others proposed that changes in the sun itself were responsible. If the sun's energy output varied over long timescales, it could drive cycles of warming and cooling on Earth. Some researchers explored the role of carbon dioxide. The Swedish scientist Svante Arrhenius had calculated in 1896 that changes in atmospheric carbon dioxide could significantly alter global temperatures. Arrhenius recognized that lower carbon dioxide levels would cool the planet and higher levels would warm it. But no one yet understood what might cause carbon dioxide to rise and fall cyclically. Mountain building was another proposed mechanism. When large mountain ranges like the Himalayas rose, they exposed fresh rock to weathering. Chemical weathering absorbs carbon dioxide from the atmosphere, potentially triggering cooling. Each theory had its strengths, each had its weaknesses, and none of them alone could fully explain the precise 100,000-year rhythm that was becoming ever clearer in the geological record. Milankovitch continued refining his work through the 1930s and 40s. He published his magnum opus, Canon of Insulation of the Earth and its application to the problem of the ice ages, in 1941. It was released in German during World War II and received little immediate attention. The world was focused on survival, not orbital mechanics. The book languished in obscurity for years. After the war, Milankovitch's theory faced increasing criticism. New geological evidence seemed to contradict his predicted timing of ice ages. Several prominent scientists declared the orbital theory dead and buried. Milankovitch died in 1958, his life's work largely rejected by the scientific mainstream. He had devoted decades to solving the mystery of the ice ages, and the answers seemed to have eluded him. But science has a way of resurrecting good ideas. In laboratories and on research vessels around the world, new technologies were emerging that would finally allow scientists to test Milankovitch's predictions properly. Deep-sea drilling was becoming more sophisticated. Isotope analysis was becoming more precise. And the first electronic computers were beginning to handle calculations that would have taken Milankovitch years to perform. The tools to solve the mystery of Earth's hidden climate clock were finally being assembled. And a group of young scientists was about to make a discovery that would change everything. They would find the proof hidden in the shells of microscopic sea creatures buried in ocean mud. They would decode a chemical signal that recorded the waxing and waning of ice sheets across millions of years. And when they compared that signal to Milankovitch's orbital calculations, the match would be astonishing. But that breakthrough, and the profound questions it raised, awaits us in the next chapter of this story. Chapter 5. The Astronomer Who Solved the Puzzle. The year was 1912. A young Serbian engineer sat in a Belgrade cafe. He had just accepted a university position. He had no idea that a single conversation would change his life forever, and through his life, our understanding of the entire planet. His name was Milutin Milankovitch. He was brilliant with numbers. He could hold enormous calculations in his mind. He was trained in civil engineering. He had built bridges and dams across the Austro-Hungarian Empire. But bridges bored him. He wanted a grander problem, something worthy of a lifetime, something no one else had dared to calculate. That night in the cafe, he found it. He would compute the climate of every planet in the solar system. It sounds impossible. It nearly was. But Milankovitch believed that mathematics could explain everything. If you knew the geometry of a planet's orbit, you could calculate the sunlight it received. If you knew the sunlight, you could predict the temperature. He began with Mars, then Venus. Then he turned his attention to Earth, and Earth presented the deepest puzzle of all. because Earth's climate had not remained constant. It had swung between extremes, between warmth and terrible cold, between green forests and miles of ice. James Kroll had tried decades earlier to connect orbital variations to ice ages. Kroll was a self-taught genius. He recognized that Earth's orbit was not fixed. It wobbled and stretched over thousands of years. These changes altered the distribution of sunlight across the globe. But Kroll lacked the mathematical tools to prove it precisely. His theory had fallen from favor. By the early 20th century, most scientists dismissed the orbital idea entirely. The ice ages seemed too dramatic to be explained by subtle shifts in geometry. Milankovitch disagreed. He believed Kroll's intuition was correct, but his calculations were incomplete. What was needed was not a new idea. What was needed was relentless precision. And precision was exactly what Milankovitch could deliver. He set to work, day after day, year after year. He filled notebook after notebook with figures. He calculated how every orbital parameter affected sunlight at every latitude for every season. No computer existed. Every number was produced by hand. Then the world interrupted him. In 1914, war erupted across Europe. Milankovitch was arrested by the Austro-Hungarian authorities. He was a Serbian national living in enemy territory. He was sent to an internment camp in Budapest. But something remarkable happened. A colleague intervened. Milankovitch was granted access to the Hungarian Academy of Sciences. In the reading rooms of that great library, while Europe destroyed itself, he continued calculating the mathematics of ancient sunlight. Think about that for a moment. Armies clashed across continents. Millions died in trenches. And one man sat quietly with pencil and paper, computing how the tilt of Earth's axis 100,000 years ago determined whether snow would melt or persist. He worked through the entire war. When peace returned, he kept working. He corresponded with other scientists. Two names became especially important: Vladimir Köppen, the great German climatologist, and Alfred Wegener, the man who proposed continental drift. Köppen recognized something crucial in Milankovitch's calculations. The key was not winter cold. The key was summer warmth. Specifically, the intensity of summer sunlight at high northern latitudes. This was the trigger that mattered. If northern summers were warm enough, winter snow would melt each year. The land would stay dark. It would absorb heat. But if northern summers were cool, snow would survive. White snow would reflect sunlight. The land would grow colder. Köppen urged Milankovitch to focus on 65 degrees north latitude. This was the critical zone. Northern Canada, Scandinavia, Siberia, the places where ice sheets were born. Milankovitch recalculated everything with this focus. The results were stunning. His curves showed regular oscillations in summer sunlight at 65 north. These oscillations matched the known timing of ice ages with surprising accuracy. When summer sunlight dipped, ice advanced. When it rose, ice retreated. Milankovitch published his masterwork in 1941. He called it Canon of Insulation of the Earth and its application to the problem of the ice ages. It was dense. It was mathematical. It was largely ignored. The world was at war again. Yugoslavia was invaded. Milankovitch watched his country torn apart. His great theory sat in libraries unread. Few scientists had the patience to work through his enormous tables of numbers. Some who did read it were skeptical. The orbital changes seemed too small. The variations in sunlight amounted to only tiny percentages. How could such subtle shifts produce mile-thick ice sheets covering entire continents? Something seemed to be missing. Milankovitch grew old. He continued working, but recognition never came. He died in 1958 in Belgrade. He was 79 years old. His theory was considered an interesting curiosity by most. A clever, but probably wrong idea. He never learned that he was right. He never saw the proof that would emerge from the bottom of the ocean. He never knew that microscopic shells buried in deep sea mud would confirm his life's work with breathtaking precision. But that proof was coming. Scientists were already beginning to drill into the ocean floor. They were pulling up long tubes of sediment, and hidden within those tubes was a record of climate stretching back millions of years. The evidence Milankovitch needed was waiting. It had been waiting for a very long time, buried under miles of dark water, written in the chemistry of creatures too small to see, and it would change everything we thought we knew. But before we can understand what they found in those ocean cores, we need to understand exactly what Milankovitch was calculating. We need to understand the three great movements that govern Earth's path around the Sun. Because Earth does not orbit simply. It wobbles, it tilts, it stretches. And each of these movements operates on a different timescale. Together, they create a complex rhythm. A rhythm that pulses through deep time like a slow heartbeat. Chapter 6. The three movements of Earth's orbit. Imagine you are floating in space. You are watching Earth orbit the Sun. From this distance, everything looks stable. Earth circles the Sun once per year. The same orbit. The same path. Dependable. Predictable. But watch for 10,000 years. Then you will see. Earth's orbit is not fixed. It shifts in three distinct ways. Each shift is slow. Each is subtle. But each changes how sunlight falls upon the planet. And those changes accumulate over millennia into enormous consequences. The first movement is called eccentricity. It describes the shape of Earth's orbit. Sometimes the orbit is nearly circular. Sometimes it stretches into a more elongated ellipse. This stretching happens on a cycle of roughly 100,000 years. When the orbit is nearly circular, Earth stays about the same distance from the Sun all year. When the orbit is more elliptical, the difference between closest approach and farthest distance grows larger. This changes total sunlight received across the year. But here's the strange part. Eccentricity produces the smallest change in sunlight of all three movements. The variation is tiny, less than 1%. And yet the Ice Age cycle matches the 100,000-year eccentricity rhythm almost perfectly. This is the 100,000-year problem. It haunted scientists for decades. The weakest orbital signal produces the strongest climate response. How? Why? The answer lies in how the three movements interact. But we will return to that mystery. The second movement is called obliquity. This describes the tilt of Earth's axis. Right now, Earth tilts about 23.5 degrees from vertical. This tilt is why we have seasons, summer in one hemisphere, winter in the other. But the tilt does not stay constant. Over a cycle of roughly 41,000 years, it swings between about 22 degrees and 24.5 degrees. A difference of only 2.5 degrees. It seems trivial. It is not trivial. When the tilt increases, summers become more extreme. More sunlight hits the polar regions during summer. Winters also become more extreme. But the key effect is on summer warmth near the poles. Greater tilt means warmer polar summers. Warmer polar summers melt more ice. So when obliquity is high, ice sheets tend to retreat. When obliquity is low, polar summers are cooler and gentler. Snow survives more easily. Ice accumulates. This was precisely what Köppen told Milankovitch to focus on. Before around 1 million years ago, ice ages followed the 41,000-year obliquity cycle almost exclusively. The rhythm was clean and clear. Tilt changed. Ice responded. The system was relatively straightforward. Then something shifted. The cycle lengthened to 100,000 years. The third movement is called precession. This is the most complex. Imagine Earth's axis as a spinning top. As the top spins, it also wobbles slowly. The axis traces a circle in space. One complete wobble takes roughly 26,000 years. Precession changes which season occurs when Earth is closest to the Sun. Right now, Earth is closest to the sun during northern winter. This makes northern winters slightly milder and northern summers slightly cooler. The effect is modest but real. 13,000 years from now, precession will bring Earth closest to the sun during northern summer instead. Northern summers will be warmer. Northern winters will be colder. The seasons will be more extreme in the north and gentler in the south. This matters enormously because most of Earth's large land masses are in the northern hemisphere. Canada, Siberia, Scandinavia. These are the ice sheet nurseries. When precession delivers cool northern summers, snow survives. When it delivers warm northern summers, snow melts. Now here is where it gets beautiful and complicated. These three movements do not operate independently. They interact. They reinforce each other sometimes. They cancel each other out at other times. The result is a complex interference pattern of sunlight variation. Imagine three musicians playing simultaneously. One plays a slow deep note cycling every 100,000 years. Another plays a middle note cycling every 41,000 years. The third plays a higher note cycling every 26,000 years. Together they create a chord. Sometimes the notes align. All three movements conspire to reduce northern summer sunlight at the same moment. When this happens, the effect is powerful. Snow survives. Ice grows. The planet cools. These moments of alignment are when ice ages begin. Sometimes the notes oppose each other. One movement pushes toward warmth, while another pushes toward cold. The effects partially cancel. Climate remains in an intermediate state. Neither full glaciation nor full warmth. A kind of climatic ambiguity. Milankovitch computed all of this by hand. He calculated the combined effect of all three movements on sunlight intensity at every latitude. He produced curves showing how insolation changed over hundreds of thousands of years. The work was monumental. His curves showed a pattern. Deep dips in northern summer sunlight corresponded to known ice ages. Peaks in sunlight corresponded to warm interglacial periods. The match was suggestive. It was tantalizing, but it was not yet proof. The problem was dating. In Milankovitch's time, scientists could not precisely date when ice ages had begun and ended. Geological evidence was crude. Moraines and till deposits told you glaciers had existed, but not exactly when. The timeline was fuzzy. Without precise dates, you could not truly test the theory. You could not say with confidence that a particular dip in the sunlight curve corresponded to a particular glaciation. The match might be coincidence. Skeptics said exactly this. What was needed was a continuous, unbroken climate record stretching back hundreds of thousands of years. A record with precise dating. A record that captured every advance and retreat of ice. Such a record seemed almost impossible to obtain. But it existed. It had been accumulating for millions of years on the ocean floor, layer by layer, century by century, written not in rock or soil, but in the shells of tiny creatures called foraminifera, creatures that lived and died and sank. Each shell contained a chemical signature, a ratio of oxygen isotopes that recorded the temperature and ice volume of the world at the moment the creature lived. Billions of shells. Millions of years. An archive of staggering completeness. No one had yet read this archive with sufficient precision. No one had yet drilled deep enough or analyzed carefully enough or dated accurately enough. But the tools were being developed. The scientists were gathering. The moment of revelation was approaching. The orbital theory made a specific prediction. It said ice ages should follow a rhythm composed of three frequencies: 100,000 years, 41,000 years, 26,000 years. Find those frequencies in the climate record, and the theory would be confirmed. Fail to find them, and decades of calculation would be meaningless. Milankovitch's life work would join the long list of elegant theories that nature simply does not obey. Everything depended on what the ocean floor would reveal. But even if the frequencies were confirmed, a deeper puzzle would remain. Why does the climate system amplify such tiny orbital signals into such enormous responses? What turns a 1% change in sunlight into a mile of ice? The answer involves feedback loops, mechanisms that take a small push and multiply it relentlessly, mechanisms that transform a whisper into a roar. And understanding these feedbacks is essential to understanding why ice ages grow so slowly and then collapse so suddenly. Chapter 7. Why Ice Ages Grow Slowly, Then Collapse. There is something deeply strange about ice ages. They do not come and go symmetrically. They build gradually over tens of thousands of years, layer upon layer, century after century. The ice grows with terrible patience. Then it collapses in a geological instant. The last ice age took roughly 90,000 years to reach full intensity. The ice sheets grew from nothing to miles thick. They covered continents. They locked up so much water that sea levels dropped 400 feet. Then in roughly 10,000 years, it was over. This asymmetry is one of the great puzzles of climate science. If orbital changes alone drove ice ages, you would expect growth and collapse to be roughly equal in duration. The orbital curves are smooth and gradual in both directions. But ice ages are not. The answer lies in feedback loops. A feedback loop occurs when a change in the system triggers additional changes that either amplify or dampen the original change. In the case of ice ages, the dominant feedbacks are amplifying. They make things worse. The most powerful feedback is ice albedo. Albedo means reflectiveness. Fresh snow is the most reflective natural surface on Earth. It bounces roughly 90% of incoming sunlight back into space. Dark ocean water absorbs 90%. The difference is enormous. Imagine northern summer sunlight decreasing slightly due to orbital changes. A little more snow survives the summer. The ground is now slightly whiter than before. It reflects slightly more sunlight. The region cools slightly more. Next winter, even more snow accumulates. This is a positive feedback loop. More snow leads to more cooling, leads to more snow. The initial orbital push is small, but the albedo feedback amplifies it relentlessly. Each year the effect compounds. The white patch grows. The cooling deepens. Over centuries, the surviving snow compresses into ice. The ice sheet thickens. It spreads southward. As it spreads, it covers more dark ground with white surface. The albedo effect grows stronger. The cooling accelerates. The ice sheet becomes self-sustaining. Now a second feedback engages. As the planet cools, the oceans absorb more carbon dioxide from the atmosphere. Cold water holds dissolved gases more effectively than warm water. The atmosphere loses carbon dioxide. With less carbon dioxide, the greenhouse effect weakens. Less greenhouse warming means more cooling. More cooling means colder oceans. Colder oceans absorb more carbon dioxide. The atmosphere loses still more of its insulating gas. This is another positive feedback loop. It amplifies cooling alongside the albedo effect. A third feedback involves vegetation. As ice sheets advance and temperatures drop, forests retreat. Trees are replaced by tundra and bare ground. Living forests are relatively dark. They absorb sunlight effectively. Tundra and bare ground are lighter. They reflect more sunlight. The loss of forests further increases surface albedo. The planet reflects more energy. Temperatures drop further. More forest dies. More tundra spreads. Another amplifying loop. Each feedback reinforces the others. The system cascades toward cold. There are still more feedbacks. Ice sheets grow so massive that they change atmospheric circulation patterns. They deflect the jet stream. They create their own weather systems. Dry, cold winds blow off the ice. These winds suppress precipitation in surrounding areas. Paradoxically, the ice sheets themselves become so cold and dry that they receive little new snowfall. Their growth slows. They persist not because snow is falling heavily upon them, but because temperatures are so low that virtually nothing melts. They endure through cold, not accumulation. The oceans also change profoundly during glaciation. Ocean circulation patterns shift as temperature gradients steepen. The great conveyor belt of ocean currents slows or redirects. Warm water that once reached the North Atlantic is diverted. Northern Europe grows even colder. Dust increases dramatically during ice ages. Ice core records show glacial atmospheres thick with windblown dust. Dry exposed continental shelves and unvegetated landscapes release enormous quantities of fine particles. This dust can both cool and warm depending on where it settles. On ice sheets, dust has a complicated effect. Light-colored dust increases albedo slightly, but dark dust decreases albedo. When dust settles on ice, it can darken the surface and increase melting. This becomes important later, during the collapse phase. All of these feedbacks work together to amplify the modest orbital signal into a continental transformation. Milankovitch's calculation showed that summer sunlight at 65 north might decrease by only a few %. But feedbacks multiplied that signal by factors of 5 or 10. This explains the slow growth phase. Orbital changes nudge the system gently. Feedbacks engage one by one. Each reinforces the others. The ice builds incrementally. It takes tens of thousands of years because the feedbacks operate slowly. Oceans absorb carbon dioxide gradually. But why does collapse happen so quickly? Why do ice ages end in a rush? The answer lies in the same feedbacks operating in reverse, but with one critical difference. The ice sheet itself becomes unstable at a certain point. As orbital parameters shift toward warmer northern summers, sunlight increases at 65 north. The edges of the ice sheet begin to melt. Meltwater darkens the surface. Dust accumulated over millennia is exposed. Dark pools form on the ice. Albedo drops rapidly. Now the feedbacks reverse with terrifying speed. Less ice means less reflection. More sunlight is absorbed. More melting occurs. Warming oceans release carbon dioxide back into the atmosphere. The greenhouse effect strengthens. Temperatures rise faster. Forests recolonize formerly barren land. There is another mechanism unique to collapse. Ice sheets become so thick and heavy that their bases melt from geothermal heat and pressure. The ice begins sliding on a layer of meltwater. Enormous sections can surge forward into the ocean and disintegrate. This is catastrophic. Marine ice sheet instability is one of the fastest mechanisms of deglaciation. When ice sheets extend into the ocean, warm water attacks their bases. Floating ice shelves break apart. Without the buttressing effect of these shelves, glaciers accelerate dramatically. They pour ice into the sea. The combination of surface melting, glacial sliding, marine instability, rising carbon dioxide, expanding forests, and decreasing albedo creates a cascade. Collapse feeds collapse. What took 90,000 years to build disappears in 10,000. The asymmetry is explained by feedback dynamics. But this explanation raises a haunting question. If the system is driven by feedbacks that amplify small signals, then it is inherently sensitive. It does not require a large push to change dramatically. It requires only the right push at the right moment. And this is precisely what Milankovitch's theory proposes. Orbital changes provide the pacing. Feedbacks provide the power. The orbit is the conductor. The feedbacks are the orchestra. The conductor gives a subtle cue. The orchestra produces a thunderous response. This framework explains something else that puzzled scientists. Ice core records show that carbon dioxide changes lag slightly behind temperature changes during glacial cycles. Skeptics argued this proved carbon dioxide did not cause ice ages. They were missing the point entirely. Carbon dioxide is not the initial trigger. Orbital changes trigger the cycle, but carbon dioxide is a crucial amplifier. As temperatures begin to drop, oceans absorb carbon dioxide. This removes greenhouse gas from the atmosphere and amplifies the cooling. The lag is expected. During warming phases, the same logic applies in reverse. Temperatures begin rising due to orbital changes. Warming oceans release carbon dioxide. The released carbon dioxide amplifies the warming. Carbon dioxide is both a feedback and an amplifier. Its role is secondary but essential. Without the carbon dioxide feedback, orbital changes alone would produce only modest temperature swings, perhaps 2 or 3 degrees. With the carbon dioxide feedback, swings reach 8 to 12 degrees in polar regions. The difference between a cool summer and an ice age. Now consider our current moment. We are in interglacial period. Orbital parameters suggest that without human influence, the next glaciation would begin in roughly 50,000 years. Summer sunlight at 65 north is slowly declining. The natural trajectory points toward ice. But we have added something unprecedented. We have increased atmospheric carbon dioxide by 50% in less than 2 centuries. We have overwhelmed the carbon dioxide feedback that normally takes millennia to operate. We have pushed the amplifier to maximum before the conductor raised a baton. What does this mean for the glacial cycle? As human activity permanently altered the rhythm that has governed climate for millions of years, can a civilization override an astronomical cycle? These are questions that emerge directly from understanding the feedback system. But they are questions for another time, because there is a more immediate story still to tell. A story about proof. About the moment when theory became fact. When the ocean floor surrendered its secrets and Milankovitch was vindicated at last. In 1976, 3 scientists published a paper that changed everything. They had analyzed deep-sea sediment cores with unprecedented precision. They had extracted the climate signal from oxygen isotopes locked in ancient shells. And what they found was exactly what Milankovitch had predicted. 3 frequencies, 100,000 years, 41,000 years, 23,000 years. The orbital pacemaker of the ice ages, confirmed beyond reasonable doubt. The paper was titled Variations in the Earth's Orbit, Pacemaker of the Ice Ages. It landed like an earthquake. But confirmation brought its own mysteries. Mysteries that were deeper and stranger than anyone expected, because the match was almost too good. And the dominant frequency, 100,000 years, was driven by the weakest orbital force. Something else was at work. Something hidden in the feedback loops. Something about the ice sheets themselves. Something about how they grew and collapsed that science had not yet grasped. The proof opened a door. And behind that door was a darkness full of new questions. Chapter 8. How Ice Ages Shaped Human Evolution. 100,000 years ago, the ice returned. It did not arrive with thunder or warning. It came as a slow cooling, a gradual shortening of summers, a quiet thickening of snow that refused to melt. And in that silence, everything changed for our ancestors. We have spent this journey understanding the machinery of ice ages, the orbital cycles, the feedback loops, the deep-sea evidence locked in microscopic shells. Now we must ask the most personal question of all. What did these cycles of cold do to us? The answer is profound. Ice ages did not merely test humanity. They built humanity. Every capacity you possess for language, planning, creativity, and cooperation was forged in the crucible of climate instability. You are, in the deepest sense, a child of ice. Consider the world our ancestors inhabited. Africa 100,000 years ago was not the Africa of today. The Sahara expanded and contracted like a breathing organism. Lakes appeared and vanished across millennia. Forests shrank into isolated patches surrounded by vast grasslands. These changes were not random. They followed the orbital rhythms Milankovitch calculated. When precession shifted monsoon patterns, rainfall moved. When obliquity changed, temperature gradients shifted. Africa danced to the same celestial music as the northern ice sheets. But Africa responded differently. Instead of ice, it produced drought. Instead of glaciers, it created expanding deserts. The Sahara became an impassable barrier. Then it became a green corridor, then a barrier again. Each cycle reshuffled the landscape. Human populations responded by fragmenting. Groups became isolated in ecological refugia, small pockets of habitable land surrounded by hostile terrain. These islands of survival dotted eastern and southern Africa. Each group evolved slightly differently. Geneticists can see this fragmentation in our DNA today. The deepest branches of human genetic diversity exist within Africa. Some lineages diverged over 300,000 years ago. They came back together and split apart repeatedly, driven by climate oscillations. This process has a name. It is called the pulsed dispersal model. Climate shifts pushed groups apart during dry periods. Wet periods reconnected them. Each reunion mixed genetic and cultural innovations. Each separation allowed new adaptations to develop. Think of it as a rhythm: isolation, innovation, reconnection, sharing, then isolation again. Each pulse produced something new: a better stone tool technique, a more complex social structure, a new way of communicating. Climate was the composer. The archaeological record supports this beautifully. Around 100,000 years ago, sophisticated behaviors appear and disappear across Africa. Shell beads emerge at Blombos Cave in South Africa. Complex tools appear at Howiesen's port. Then they vanish for thousands of years. These disappearances puzzled scientists for decades. Why would human groups develop advanced technology and then lose it? The answer lies in population size. When climate deteriorated, groups shrank. Small populations cannot maintain complex cultural knowledge. Skills disappeared with the people who held them. But when climate improved and populations reconnected, innovation spread rapidly. Each warm period saw a ratcheting upward of human capability, not a smooth ascent, a stuttering, pulsing climb driven by the rhythm of orbital cycles. The ice ages also shaped our bodies. Human skeletal proportions follow climate rules observed across mammals. Populations in colder regions developed shorter, stockier builds to conserve heat. Populations in tropical regions maintained longer, leaner frames to dissipate heat efficiently. But the deepest changes were cognitive. Unpredictable environments favor flexible thinking. Animals in stable environments can rely on fixed instincts. Animals facing constant change need the ability to plan, innovate, and imagine scenarios that have not yet occurred. This is exactly what the Ice Age world demanded. Our ancestors could not simply follow the same routine each year. The landscape kept changing. Food sources shifted. Water availability fluctuated. Survival required mental models of a world in constant flux. Language likely evolved under these pressures, communicating about things not immediately present, warning about dangers remembered from previous seasons, planning hunts for animals whose migration routes had shifted, sharing knowledge about water sources discovered during previous wet periods. Cooperation intensified for the same reasons. A lone individual or isolated family could not survive prolonged drought. Networks of exchange became essential. Groups that shared food, information, and mating partners across wide areas survived. Those that remained isolated perished. The Great Exodus from Africa around 70,000 years ago was itself a climate story. A severe glacial period dried much of Africa. Simultaneously, lower sea levels exposed coastal routes. Small groups followed shorelines out of Africa and into Asia. They carried with them the cognitive toolkit forged by millennia of climate instability, flexible thinking. complex language, social cooperation, symbolic thought. These were not luxuries. They were survival adaptations hammered into shape by the relentless rhythm of ice. Every population they encountered, every new environment they entered, those Ice Age skills proved decisive. Neanderthals possessed many impressive adaptations, but the cultural flexibility of African-evolved modern humans, shaped by more extreme climate variability, gave them a persistent edge. The Ice Ages did not merely happen to us, they made us. The orbital cycles that Milankovitch calculated are written into our genome, written into our capacity for art and language, written into our restless need to explore, adapt, and imagine what lies beyond the horizon. You exist because ice advanced and retreated, because summers cooled and warmed, because the Earth wobbled on its axis and tilted toward and away from the sun. You are the answer that evolution found to the question the ice kept asking. Chapter 9. Why our current warm period exists. Everything we have explored leads to a single remarkable fact. You are living in an anomaly. The warm, stable climate you experience every day is not normal. It is a brief interruption in a world that has spent most of the last million years buried under ice. This interruption has a name. It is called the Holocene. It began approximately 11,700 years ago when the last great ice sheets finally retreated from North America and Europe. It continues today, and its stability is unlike anything in the recent geological past. To understand why the Holocene exists, we must return to the orbital cycles one final time. Approximately 20,000 years ago, the Earth sat at the depth of the last glacial maximum. Ice sheets 3 kilometers thick covered Canada and Scandinavia. Sea levels set 400 feet below today. Then the orbital parameters shifted. Precession brought northern hemisphere summer closer to the sun. Obliquity increased axial tilt. Summer sunlight at 65 degrees north intensified. The trigger that Milankovitch identified fired, but this time in reverse. Melting began. The melting was not smooth. It came in violent pulses. Around 14,700 years ago, a massive surge of meltwater flooded into the North Atlantic. This event disrupted ocean circulation. Europe, which had been warming, suddenly plunged back into near glacial cold. This cold snap is called the Younger Dryas. It lasted over 1,000 years. Glaciers advanced in Scotland and Scandinavia. Forests retreated. Animals that had moved north were driven south again. It was a brutal reminder that climate transitions are rarely gentle. Then, around 11,700 years ago, the Younger Dryas ended. It ended with astonishing speed. Ice cores from Greenland showed that temperatures rose by roughly 10 degrees Celsius in a single decade, perhaps less. The speed is almost incomprehensible. The world transformed within a human lifetime. Ice retreated. Forests surged northward. Sea levels rose rapidly, flooding coastal plains and separating islands from continents. Britain detached from Europe. Australia separated from New Guinea. The geography of the modern world took shape. What followed was unprecedented. For the next 11,000 years, global temperatures remained remarkably stable, variations of perhaps 1 degree Celsius in either direction. Compared to the wild swings of glacial periods, this was extraordinary flatness, a calm plateau. No one fully understands why the Holocene has been so stable. Orbital forcing alone does not explain it. The current orbital configuration is actually rather modest. We are not at an extreme of any cycle. Summer sunlight at northern latitudes has been slowly declining for thousands of years. Some scientists credit the residual effects of the massive deglaciation itself. The redistribution of water, the recovery of vegetation, the stabilization of ocean circulation patterns. These processes may have created a self-reinforcing equilibrium that has persisted far longer than orbital mechanics alone would predict. Others point to an intriguing coincidence. The Holocene is the period during which humans began farming. Agriculture produces methane from rice paddies and livestock. Deforestation releases carbon dioxide. William Rudiman has argued that early agriculture may have prevented a natural cooling that should have already begun. This is a provocative idea. It suggests that humans may have been inadvertently modifying climate for thousands of years. Not enough to cause dramatic warming, but enough to maintain the Holocene's remarkable stability. Enough to delay the next glaciation before anyone understood what glaciation meant. Regardless of the cause, the Holocene's stability made everything possible. Consider what humanity accomplished in this narrow window. Agriculture, cities, writing, mathematics, philosophy, industry, spaceflight. None of it occurred during a glacial period. All of it happened in this one warm pause. This is not coincidence. Agriculture requires predictable seasons. Crops need reliable rainfall patterns. Rivers must flood and recede on schedules that farmers can anticipate. The chaotic climate of glacial periods made such predictability impossible. Only Holocene stability allowed the experiment of civilization. Think about what this means. Every empire that rose and fell did so within this single interglacial. Every language ever written was composed during this warm interval. Every scientific discovery occurred under these specific climatic conditions. The Holocene is the entire stage upon which human civilization performed. Previous interglacials lasted different durations. The Eemian interglacial, before the last ice age, lasted roughly 15,000 years. Some interglacials were shorter. Some were longer. There is no fixed duration. The Holocene has already lasted nearly 12,000 years. During the Eemian, global temperatures were slightly warmer than today. Sea levels were 6 to 9 meters higher. Hippopotamuses lived in the Thames River. Forests covered areas that are now tundra. It was a world similar to ours but subtly different, and it ended. The Eemian ended because orbital parameters shifted. Northern summers cooled just enough. Snow began accumulating in northern Canada and Scandinavia. Feedback loops engaged. Ice sheets grew. Within a few thousand years, the world had plunged back into full glaciation. The cycle continued. Scientists studying the Eemian have found evidence of rapid climate oscillations, even within that interglacial. Brief cold snaps and warm surges. The Holocene, by comparison, has been unusually quiet. We may be living in the most stable climate period of the last several 100,000 years. This stability is the invisible foundation beneath everything you know. Your food supply depends on it. Your city's location depends on it. The coastline you recognize depends on it. Remove this stability, and the structures of civilization become impossible to maintain. And yet, this stability is temporary. The orbital cycles have not stopped. The Earth continues to wobble and tilt and stretch its orbit. The same celestial mechanics that ended the Eemian will eventually end the Holocene. The only questions are when, and whether something else intervenes first. Those questions have haunted climate scientists for decades. The orbital calculations are clear. The feedbacks are understood in principle, if not in detail. The deep sea record provides a timeline of past transitions. Everything points toward an inevitable conclusion. But the conclusion is more complicated than anyone expected. Because something unprecedented has entered the equation. Something no previous interglacial ever faced. And it changes everything we thought we knew about what comes next. We are almost ready to face that question directly. The question of when. The question of whether. The question that connects orbital mechanics to human agency in ways that Milankovitch could never have imagined when he sat in that Budapest library, calculating by hand. Chapter 10. When the next ice age should begin. This is the question we have been building toward across the entire journey. Through 100,000 years of ice. Through the orbital cycles of Milankovitch. Through deep sea cores and oxygen isotopes and feedback loops. When does the next ice age begin? The answer requires us to think on two timescales simultaneously. The geological timescale, measured in tens of thousands of years, and the human timescale measured in decades and centuries. These timescales are colliding right now in our lifetimes in ways that are unprecedented in Earth's history. Let us begin with what the orbital cycles predict. The current orbital configuration places us in a period of relatively low eccentricity. The Earth's orbit is nearly circular. This means the difference between closest and farthest solar approach is small. Seasonal extremes driven by orbital position are muted. Obliquity is currently decreasing. The axial tilt is moving from a recent maximum back toward its minimum value. This means summers at high northern latitudes will receive progressively less direct sunlight over the coming millennia. The trend favors cooler summers. The trend favors ice accumulation. Precession currently places northern hemisphere summer near the farthest point from the sun. This means northern summers receive slightly less solar energy than they would if summer coincided with closest approach. Combined with decreasing obliquity, the orbital geometry is slowly moving toward glacial conditions. André Berger, the Belgian astronomer who refined Milankovitch's calculations using modern computers, published a landmark analysis. He calculated that the current interglacial should be exceptionally long due to the specific combination of orbital parameters. The low eccentricity weakens precessional forcing considerably. Berger's calculations suggested that without human interference, the next significant glaciation would not begin for approximately 50,000 years. This is unusually long. Most interglacials last 10 to 15,000 years. The current orbital configuration grants us an extended warm period. Other researchers have reached similar conclusions using different methods. By comparing the current orbital configuration with similar configurations in the past, they identified an analog approximately 400,000 years ago. That interglacial, called marine isotope stage 11, lasted an unusually long time. Marine isotope stage 11 persisted for nearly 30,000 years before glaciation resumed. Its orbital parameters closely match our own: low eccentricity, weak precessional forcing. This parallel suggests the Holocene would naturally persist for tens of thousands of additional years before ice returned. So the natural answer to our central question is this: without human influence, the next ice age should begin roughly 50,000 years. That is the geological verdict. The orbital cycles, for once, are in no hurry. The celestial clockwork grants us an unusually long reprieve. But this answer is incomplete, because we have introduced a variable that no orbital calculation can account for, a variable that Milankovitch never considered, a variable that has no precedent in the 4.6 billion year history of this planet: industrial carbon dioxide emissions. Svante Arrhenius calculated in 1896 that doubling atmospheric carbon dioxide would raise global temperatures by roughly 5 degrees Celsius. His estimate was remarkably close to modern projections. But Arrhenius thought this warming would take thousands of years and considered it beneficial. He was wrong about the timeline. Since the Industrial Revolution, atmospheric carbon dioxide has increased from roughly 280 parts per million to over 420 parts per million. This increase has occurred in approximately 200 years, an instant in geological time. The current concentration of carbon dioxide has not been seen on Earth for at least 3 million years. During the Pliocene epoch, when carbon dioxide levels were last this high, global temperatures were 2 to 3 degrees warmer. Sea levels were 15 to 25 meters higher. The Ice Age cycle depends on a delicate balance. Small orbital changes trigger feedback loops. Those feedbacks amplify or dampen the initial signal. Carbon dioxide is one of the most powerful feedback mechanisms. It has always responded to orbital forcing. Now it is being forced independently. Climate models consistently show that current and projected carbon dioxide levels are sufficient to prevent the next glaciation entirely. Not merely delay it, prevent it. The orbital trigger requires cool northern summers. Elevated greenhouse gases keep those summers too warm for ice to accumulate. A study published in Nature in 2016 by Andrzej Ganopolski and colleagues quantified this precisely. They found that carbon dioxide concentrations above roughly 240 parts per million would prevent glaciation under current orbital parameters. We are at 420 and rising. Even if all emissions stopped today, carbon dioxide would remain elevated for thousands of years. The ocean absorbs carbon dioxide slowly. Weathering of rocks removes it over tens of thousands of years. The pulse of carbon we have released will persist in the atmosphere across geological timescales. This means the Ice Age cycle that has governed Earth's climate for 2.5 million years may have been interrupted, not by a meteor, not by volcanic eruptions, not by any natural force, by a single species that learned to burn ancient carbon stored in fossil fuels. Pause and consider the magnitude of this statement. For 2.5 million years, ice ages came and went with clockwork regularity. Orbital cycles triggered them. Feedback loops amplified them. Ice sheets grew and collapsed. Sea levels rose and fell by hundreds of feet. Entire ecosystems transformed. And now, within the span of 2 centuries, one species has potentially overridden that entire system. The same species that the ice ages themselves created. The flexible, innovative, cooperative species forged in the crucible of climate instability has now become the dominant force in the climate system. This is the great paradox at the heart of our story. Ice ages made us human. They drove our evolution. They forced us to think, cooperate, and innovate. And those very capacities eventually gave us the power to prevent ice ages from ever occurring again. Whether this is triumph or tragedy depends on what happens next. Preventing glaciation might sound beneficial. No one wants ice sheets covering New York and London. But the same emissions that prevent glaciation are producing rapid warming that carries its own catastrophic risks. The Ice Age cycle operated slowly. Glaciations developed over 90,000 years. Deglaciations took 10,000 years. Ecosystems had millennia to adapt. Species could migrate. Ocean currents could adjust. The pace allowed the biosphere to reorganize itself repeatedly without collapse. Current warming is occurring thousands of times faster than natural ice age transitions. Ecosystems cannot migrate fast enough. Coral reefs are bleaching. Permafrost is thawing, releasing stored methane. Ice sheets in Greenland and Antarctica are losing mass at accelerating rates. The pace itself is the danger. So we face a strange situation. We have likely prevented the next ice age, but we have replaced a slow, predictable, survivable cycle with a fast, unprecedented, and potentially uncontrollable transformation. We have traded one climate future for another, and we chose it without understanding what we were choosing. Milankovitch spent decades calculating the celestial mechanics of climate. He understood that Earth's temperature is governed by geometry and physics. He did not anticipate that a mathematical species would alter the equation. That human ingenuity would become a geological force rivaling orbital mechanics. The deep-sea sediment record that confirmed his theory may already be recording the anomaly. Future scientists, perhaps thousands of years from now, will examine the sediment layer we are currently depositing. They will find an unprecedented spike in carbon, an abrupt warming, a missing glaciation. They will recognize it as the moment one species rewrote the rules. The moment the Ice Age cycle, that ancient metronome that ticked for millions of years, fell silent. Not because the orbital cycles stopped. They continue their patient dance even now, but because something louder drowned them out. So here we rest, at the end of a story that spans 100,000 years. A story of ice and orbit and bone and ambition. A story that began with snow falling on silent Canadian forests and ends with carbon dioxide molecules trapping heat in an atmosphere transformed by human hands. The Ice Ages made us. They sculpted our minds for flexibility. They demanded cooperation and language and foresight. They punished rigidity and rewarded imagination. Every capacity that allowed us to build civilizations was first a survival adaptation in a world of relentless climatic change. And then we used those very gifts to change the climate ourselves. The child of ice grew up and melted its parent. This is not metaphor. It is the literal trajectory of our species. Born from glacial pressure, raised in interglacial warmth, now rewriting the atmospheric rules entirely. The orbital cycles continue. The Earth still wobbles. The tilt still oscillates. The orbit still stretches and rounds. Milankovich's celestial clockwork takes on with perfect indifference. But for the first time in 2.5 million years, the clock may strike and nothing will answer. What does it mean to be the species that stopped the Ice Ages? What responsibility comes with that power? We inherited a planet shaped by cycles far older than consciousness. Now we hold those cycles in our hands. The question is no longer what the ice will do to us. The question is what we will do without it. Somewhere beneath the North Atlantic, foraminifera are building their shells. Recording this moment in calcium carbonate. Writing a message in oxygen isotopes that scientists thousands of years from now may read. What will that message say about us? About this strange warm silence where glaciation should have been? We do not yet know the ending. The Ice Age story is not finished. It has merely entered an unprecedented chapter. One written not by celestial mechanics, but by human choice. And that, perhaps, is the most astonishing Ice Age discovery of all. The next chapter is ours to write. If this journey through deep time moved you, if it changed how you see the sky and the seasons and the fragile warmth of this present moment, subscribe to our channel. More stories like this are coming. Stories where science meets wonder and the ancient earth whispers secrets we are only beginning to hear.